Dear ladies and gentlemen, many thanks for looking up my presentation for the ICS online conference. My name is Matthijs de Rijk and I'm a PhD candidate at the Department of Urology at Maastricht University. In this presentation I would like to tell you about our parcellations of functional clusters within the human periaqueductal gray during full and empty bladder states. These are conflicts of interest. The periaqueductal gray, also known as the PAG, is a brainstem area that is indicated to be involved in both storage and voiding of urine. The PAG takes a very central location in the hierarchical system of micturition control. We have previously shown that the PAG can reliably be parcellated into functionally distinct clusters, shown in the figure on the right. We have furthermore confirmed that these parcellations show some characteristics that correspond to what would be expected based on neuroanatomical studies, meaning that these clusters are organized in a lateralized fashion, which is shown in the bottom figure. In the current study, we will assess the similarity between parcellation results of empty and full bladder states, and we expect a significant spatial overlap between the cluster constellations found in both states. For this abstract, we have evaluated data from 6 female participants. We acquired resting state fMRI data at different sensory time points. We first acquired a resting state scan with an empty bladder, and then we started filling the bladder via catheter at a filling rate of 30 milliliters per minute. And once participants indicated a strong desire to void, we started our second resting state scan. Both resting state datasets were then parcellated. We did this by identifying the PAG in the anatomical scans for each patient and drew a personalized mask of the PAG. All voxels within this mask were then put into a square connectivity matrix, which was then parcellated using the Louvain module detection algorithm. This algorithm clusters voxels with stronger within cluster connectivity than between cluster connectivity together. Using the empty bladder parcellation, we computed random parcellations with a script that randomly places an anchor point in the 3D space of the PAG masks and grows modules similar in size to the original modules from this anchor point. We iterated the script to obtain 1,000 different random parcellations. These random parcellations were then used to quantify the agreement between our observed parcellations based on fMRI data acquired during an empty and full bladder state. We used the Serison dice coefficient to statistically test the extent to which the similarity between empty and full bladder parcellations was higher than could be expected based on chance on a single subject level. For each of our participants, we found that the agreement between at least one of the clusters in both states resulting from the parcellation procedures was higher than could be expected based on chance, as can be seen in this table. The figures give an example of the similarity between empty and full bladder parcellations for a participant where we found significant counterparts for each cluster. These results indicate that PAG activity in an empty and full bladder state can reliably be parcellated into clusters that are largely independent on bladder state and show a significant similarity across these states. This implies that PAG parcellations can be used to study changes in dynamic connectivity between these clusters, which is related to bladder fullness and participants' experienced bladder sensations. This might enable us to create patient-specific PAG response profiles that could potentially help us to identify new and more optimally targeted treatment and diagnostic options for patients. I would like to thank you again for your interest in my presentation, and I'm very happy to interact with you regarding any questions you might have.